All right, hello everyone, and welcome to McLean 360. All right, so in this video, I want to solve a question with you to illustrate the concept of stress. And okay, let's read the problem together and solve it. So in this problem, each of the four vertical links has an 8 by 36 millimeter uniform rectangular cross section, and each of the four pins has a 16 mm diameter. All right, so our task is to determine the maximum value of the average normal stress in the links connecting points B and D, and then point B and C. All right, so for this problem, um, over here is actually more or less like a mechanism, right? Let's say a structure. It's actually a structure. Now, what happens here is that you kind of apply a force which is 20 kilonewton here, and then as you begin to apply the force upwards, there is going to be some sort of how do I put it? Some stress, okay, some stress in BD and then CE. Okay, so to actually look at this carefully, what you can do is that we will take A, B, C together as one, and then the linkages, so the links connecting B and D, and then C and E. So this is what you are going to get, something like this. So let me sketch it. Now think of this as, okay, something like this, okay, and then you apply a force in this direction, and that force is 20 kilonewtons, okay. Now at a distance from here to here, so let's say this is A, and then this point is B, and over here we have B, the link connecting this one. So think about this linkage as a force, which is some way coming downwards. Because if I apply a force in this direction, there is going to be some form of reactions, and then so this is 0.25 meters, and then all the way here is 0.4 meters, right? Now if I stand here, I will also experience the same force in CE. So let's call this FBC, or let's say FBD, and then FCE. So this problem now becomes a mere statics problem, where we can use equilibrium to solve. So we can actually decide to sum forces. Okay, let's solve it together. The simplest way to solve this is to take your time and then sum moment. Okay, so what are we trying to do? We want to find the stress which is in this section, but before we can get the stress BD and then the stress CE, we would have to find, so PBD over ABD, which is the area. So we need to find that P or F, let me use FBD. And that is the mere reason why we have to do this. So the simplest way to do this is to sum moment about B. Why do we sum moment at B? If we sum moment at B, it will eliminate FBD and we can find FCE. And then we will stand at C and then sum moment. Again, it will eliminate FCE and we can get FBE. Or we can also sum forces and then solve for the equation. So let's look at summation of moment. Summing moment at B, we are going to get 20 kilonewton multiplied by 0.25, and this moment is going to cause a rotation which is clockwise. So 20 multiplied by 0.25. Okay, and then this moment, this force FCE will cause a moment this way, which is also clockwise. So about B is going to be plus 0.4 FCE. Should be what? 0. So solving for this, you can see that FCE is going to be minus 20 into 0.25. Then I divide this by what? 0.4. Okay. So it means that FCE is going to be a compressive force, because the force inside there is going to be negative. So let's calculate FCE. FCE is nothing but 20 multiplied by 0.25 divided by 0.4. So that is minus 12.5 kilo newtons. So basically the force which this member can receive is minus 12.5 kilonewtons. Then let's calculate the same thing. This time round, let's use forces. Okay, we can either sum moment about C and equate it to 0. We will get FBD. Or we can also say that summation of forces for every force going up to be positive should be 0 for equilibrium. Then we can say that 20 minus FBD minus FCE is 0. From here, we can go forward and say that FBD is 20 minus FCE. Okay. If we do this, our FBD is going to be 20 minus 12.5, which is essentially plus. So that FBD is going to be 32.5 kilonewton. So you realize that FBD is positive. Meanwhile, FCE is negative. What does this tell us? So this is kind of tensile, and this one is compressive. All right. Now, having gotten this, it means we can go ahead and find the stress, because now we know the forces in B, D, and then CE. All right. So finding the stress in BD is going to be FBD divided by the area of BD. And then what is the area? The question actually said, okay, let me go back. So if you go back, or if you look at the question again, he said that he said that these vertical links, they are having effective areas of what? 8 by 36. And what? And each of the 4 pins also have what? 16 millimeter diameter. So 36 minus 16, which is 20. So 20 millimeters. So this place is supposed to be um 8 millimeters multiplied by 20 millimeters, which is um 20 multiplied by 8, and that gives us 160 millimeters squared. All right, now you get 160 millimeters squared. However, after so it's actually ABD. So ABD will be this, and then what you are going to do is that the area which we got here, we are going to multiply it by 2, which will rather be 160 multiplied by 2, which gives us 320 millimeters squared. Therefore, this part is supposed to be 320, and then this one is supposed to be 101.5 megapascal. Now, it is interesting to note that, you see, if you look at this rigid body here, you will see that there is this portion here, but there is another one at the back. So because there are two, you multiply. Okay, there's another one at the back, so it looks like this. It looks like this, and then there is another one at the back, but that one we don't see. So this one, and then the front one. Okay, all right, I think the concept is clear. But then for the stress in CE, again, it's going to be the force CE divided by the area CE. So the area CE is also going to be the same thing, which is 8 by 36. But because the CE is in compression, what this means is that whilst so this is what is going to happen. This one will come down here, but this one will kind of go inside at this section. Therefore, this FBD will experience a net difference because it is undergoing tension. All right, but tension has to do with sort of expansion. Okay, but compression has to do with compression. So in compression, you will not feel that net difference. So basically, with the compression part, you are just going to use it as the area given, which is 8 by 36. And we are doing this because the ACE part is actually in compression. Okay. All right. So I hope the concept is clear. Now, what is 8 by 36? So 8 by 36 is 288 millimeter square. And what is 288 millimeter square? Okay, let's leave it like that. Multiplied by 2, because don't forget that they are the parallel side. So 576 millimeter squared. And now sigma BD is going to be minus FCE was what? Minus 12.5. Okay. So then minus 12.5 multiplied by 10 to the power 3 divided by 576. Okay. And then what are we getting? So minus 12.5 multiplied by 10 to the power 3 divided by 576. Okay. So you are going to get minus 20.833, or let's say minus 20.83 megapascal. All right. So that is it for you. Um, we've been able to solve for the stress. Okay. So thank you very much for watching.